Theorems.
All right. Well, thanks so much, Daniel. It's a pleasure to speak in your seminar. And everyone, thanks for coming along today. So today I'm going to be speaking about the prime number theorem, and in particular, formalization of it in Lean using a new agent called Gauss. And maybe just to kind of get everyone started on the same page, so formalization is one of these long-standing challenges that people have been working on for decades, which is the goal of translating natural language, in this case, natural language mathematics, into formal kind of machine verifiable code that you can get compiler to certify that the code's working as specified. And the case we're going to be speaking about today of pure mathematics is itself just a special case of this broader objective to verify essentially arbitrary software to meet given specifications. And I guess it should be mentioned that formalization, when done at scale, can be used over and over again. So you have reuse and this kind of trustless reliability of various modular pieces fitting together. And this kind of mode of interaction opens up impact across other areas, across science and industry, especially in these sort of mission critical systems where maybe you need to certify that some. I recently met a professor who is interested in aerospace engineering and needs to make sure that certain parts fit the specifications to make sure that everything will be safe. But this is kind of a broader objective. And so today I want to speak about the use of formalization in mathematics, where the kind of current state of the field is that there is kind of a small community of expert formalizers who know the language, the code very well, and this is essentially a very scarce resource at the moment of this human expertise. And even for the experts, formalization is quite slow and difficult to accomplish mathematics at the kind of human scale of human level statements. And really, you should perhaps think about formalization in this code as maybe analogous to what programming was like in the 1960s or maybe 70s, where you have these very low-level language, maybe not quite assembly, but very subhuman in what the kind of steps consist of. And then you have these experts who really know the language inside and out and can do this effort of translating of these human level statements into something that's much more kind of subhuman. And I should also say that formalization used to be a quite niche topic in the mathematical community. And it's only very recently, I would say, there's been a lot of excitement and momentum to formalize, especially in the language of Lean. I would say championed mostly by Kevin Buzzard. So I think I was a graduate student in 2019 when I first even heard about Lean. This was a talk from Kevin about his efforts to formalize the proof of, or I guess now to do the Fermat's theorem. And Lean is not the first language for formalization in mathematics. There are others like Isabelle, Koch, Haskell, sorry, Rock, Hall, Light. Haskell's a different story, but maybe. I was reminded of the name, but I should say that there have been other languages, but those have been also kind of in these communities of practice. But really, I think Lean has been taking off much more in the mainstream in the mathematical community. And I should also mention, just as a caveat coming from pure mathematics, computer scientists have been at this a lot longer and have been interested in this goal of formal verification, of translating natural language into running code. This has been going on for much longer, for decades. So today, I really want to focus on one particular application of formalization, specifically to the prime number theorem. So in the beginning of the talk, I just want to take some time to kind of explain what the problem is, the prime number theorem, and some of its history, which actually will have some parallels later in the talk when we talk about the kind of formalization challenge of the prime number theorem, which was recently put forward by Terry Tao and Alex Kontorovich. And then talk about this recent result using Gauss, new agent for formalization. And perhaps if there's a bit of time at the end, we'll be able to speak about some kind of maybe views on how mathematics might look in the future with these tools. So I would say that our story maybe begins in the 1790s when Gauss himself was looking at tables of numbers, in particular looking at the primes, and he noticed that not only these primes seemed to be getting rarer and rarer as the numbers in the tables he was looking at were getting larger, but more specifically, he noticed that there was a actual kind of regular trend of the density of primes. So if you took numbers of size x, he was noticing that maybe there were about 1 in log x chance that the numbers of that size were going to be prime. And so the total number of primes were thinning out, but they were doing so at maybe a slow rate, this logarithmic rate. And you know, for the 1790s, there wasn't much data one could collect. So really, you might say in today's modern lingo that he did this with very little training data as a human neural network. But in the modern form, the prime number theorem, people in the community often like to consider a certain function, the so-called Chebyshev psi function, which is a weighted average. You should think of it as a weighted average over primes, where to counterbalance the density of primes, you count log p for every prime up to x, actually also prime powers. And the statement of the prime number theorem is that this kind of weighted average is essentially 1 on average. And so if you sum the log p's for prime powers up to x, this is asymptotically x. So this is a kind of precise way of formulating the statement that primes essentially occur with probability 1 over log x. And if there are any questions, you know, at any point in the talk, just feel free to shout them out. And yeah, so
Jared, I actually had a
yeah,
quick question.
sure.
So you said this is the modern way of thinking about the prime number theorem. Is that just kind of convenience, like it's related to the logarithmic derivative of zeta, or do
Yeah,
you think
precisely.
is that okay? I'm just not
And
a logarithmic number theorist, so I was wondering if you
yeah,
could
yeah,
say
exactly.
why
So this is really the most natural quantity that arises, and then you can do a simple kind of manipulation to translate this into just like actually counting primes. But yeah, as you say, this arises very naturally as like the logarithmic derivative or involving the logarithmic derivative of the zeta function. And yeah, so this theorem, the prime number theorem, was originally a conjecture in the 1800s, but was eventually proven at the end of the century by Hadamard and de L'Hopital, who proved a kind of quantitative form of this statement. So specifically, they showed that psi of x as a function behaves pretty much like x, but has an error term, or essentially has a kind of remainder term, which is growing function that's smaller than x, and you're dividing by this maybe a bit complicated looking function, the exponential of the square root of log x. And maybe if you're a number theorist, you're happy to see exponentials and logarithms and maybe double logarithms sometime popping up everywhere. So this is like a sign that you're in analytic number theory. But maybe outside of this kind of field, maybe this looks a bit kind of complicated. So it just suffices to say that this quantity is going to be smaller than x, and it's in fact going to be smaller than x over log x, or log x to the 100 power. So this is a quantity that's growing. It's smaller than any power of x over log x to the 100, say, but it is still bigger than, let's say, x to the 0.9 or 0.99. So it's in between a kind of savings of powers of log but it's weaker than savings of a power of x, a fractional power of x. And so this is kind of like this quasi regime. And so this was a classic result proved in 1896, which was really one of these kind of culminating achievements of, I should say, 19th century mathematics. And in particular, in the course of the proof, as Daniel alluded to, the key technical result is a statement about the Riemann zeta function. So this is one of the kind of famous functions of a complex variable. So we're not going to necessarily define it today, but just suffices to know that it is some function which has a definition in the complex plane, and the technical statement that they prove is that this function is never zero when the real part of the input is bigger than 1, or rather bigger than 1 minus epsilon for this function, essentially 1 over the logarithm of the imaginary part of s. And so this statement, so it's a technical statement about a particular function, the zeta function, and it built on kind of these revolutionary ideas, this program that Riemann put forward in his famous 1859 paper. So Riemann, as probably some of you know, was a geometer and devoted his whole career to writing papers in geometry, but he wrote a single paper in 1859 on number theory, which in one fell swoop essentially changed the course of the whole field, in which, in particular, so he proposed a relationship between the distribution of prime numbers and the location of zeros of the so-called zeta function. So linking number theory with complex analysis in kind of one fell swoop. And also along the way, he proposed the famous Riemann hypothesis. So really in 8 pages, he did really a ton of work to advance the field. And the prime number theorem, when it was eventually proven by Audemars and de Villers-Poussin, really kind of makes use of a lot of cutting-edge techniques at the time, 19th century, coming from this hot new field of complex analysis. So as I mentioned, the Riemann hypothesis, this is one of the kind of greatest open problems in mathematics, is a statement that the kind of zeros, the location of the zeros of the zeta function, all should lie on this so-called 1/2 line. So that's, if you look in the complex plane and you look at all complex numbers whose real part is equal to 1/2, this corresponds to a vertical line here, kind of denoted in blue. And just for comparison, this statement of the so-called zero-free region for zeta is saying essentially that there are no zeros in this green region where the real part of s is bigger than 1. And actually, it's a little bit stronger a statement that if you just cut out a sliver, a region close to 1, even to the left, it's still, there are no zeros in that region. And so Riemann, so one can view the prime number theorem as a kind of weak approximation towards the Riemann hypothesis. And the reason Riemann was motivated to formulate his hypothesis is because he identified a very explicit relationship between the distribution of primes and the location of zeros of zeta. And in particular, if the Riemann hypothesis is true, this would imply a stronger statement along the lines of the prime number theorem, which would say that our function psi of x, this Chebyshev psi function, is equal to x, but now essentially the error term, the remainder, is like the square root of x, or 1/2 x to the 1/2 plus epsilon. And it is no coincidence in the Riemann hypothesis that you have this 1/2 line, so this constant of 1/2 is the very same constant that appears in the exponent in the error term of 1/2, or 1/2 plus epsilon. So there is a particular so-called Riemann von Mengelt explicit formula which relates the location, at least of the real parts of the zeros, to the size of the error term that you get in a kind of prime number theorem statement. And for this reason, and many others actually, the Riemann hypothesis would have this kind of direct impact on understanding the distribution of prime numbers. And it should also be said that this kind of square root of this kind of square root error term, like the exponent of 1/2, is the best possible. because there's actually a symmetry relationship in the zeta function, that if you have a zero of the zeta function, let's say at some point, then there is a reflection upon this 1/2 line to get a corresponding zero of the zeta function on the other side of the half line. And so in particular, if there are zeros that are bigger, or that real part is bigger than 1/2, then there's going to be ones that are going to be less than 1/2, and vice versa. And the Riemann hypothesis is the statement that all the zeros should lie on this kind of line of symmetry, so that really the zeta function should really embody a lot of kind of intrinsic symmetry, which is motivating a lot of work in number theory and probably also other areas which have been kind of generalized since then. So I should also mention that kind of in the history, since the kind of classical proof of the prime number theorem was given, I think it quickly became like a dogma in the field that this should be the case. And in particular, in the 20th century, the famous mathematician G.H. Hardy famously asserted that the prime number theorem was such a kind of advanced and sophisticated theorem result that any proof of it should require using complex analysis. And so this quickly became the kind of dogma in the field, but in 1949, it came as a great shock to the community when Selberg and Erdős proved the prime number theorem only using elementary methods, specifically meaning that they didn't use complex analysis. They found a different way of getting a proof. In particular, they showed kind of weaker form of the prime number theorem. So without using complex analysis, they were able to kind of only obtain a weaker kind of result in the form as follows, where our function psi of x, the Chebyshev psi function, is growing like x with some unspecified error term that is tending to 0 relative to x. So it doesn't, their proof doesn't tell you any quantitative information about how small this error term is, just that it is smaller than the main term. And so there's a kind of parallel story to having a complex analytic proof and then an elementary proof. So now fast forward to the talk we're going to speak about today. In particular, a year and a half ago, Terry Tao and Alex Kontorovich announced a project to formalize the proof of the prime number theorem in Lean. And so it should be said that this was announced in January, and already by February, so 1 month later, they had proven in Lean the kind of weak version of the prime number theorem of Selberg and Erdős, getting kind of some qualitative error, and the rest of the project was then devoted to proving this kind of classical error term using complex analysis.
So did they formalize the Erdős-Selberg proof, or was it also a complex analysis proof?
Yeah, so from my understanding, this short proof doesn't use complex analysis at all. And they were able to do this like very quickly within like a month. And then the rest of the kind of work was devoted to kind of proving the kind of more quantitative form of the error term. And in July this past year, so after 18 months of the project, Alex and Terry announced that they had proven a so-called medium strength of the prime number theorem. So they proved something that was a bit weaker than the classical error term. So they proved a form of the prime number theorem where they had replaced the kind of square root of log x with log x to the 1/10th power. And so this is, using an exponent that's smaller, but it turns out for many applications, this is still kind of this kind of quasi-polynomial where it's will give you a lot of applications that you might want. But talking to Alex, he essentially told me that they were able to do this because they found kind of a shortcut in the proof that used kind of some minimal complex analysis that was kind of supported already by the library, but really was kind of avoiding these core difficulties, namely of this kind of zero-free region for the zeta function. And this was still very much kind of like a technical obstacle that they were working on. I should also mention, so Alex, in his kind of post, he displayed what's known as a dependency graph. And so in the course of proving results in Lean and kind of getting formal proofs, the community has built up maybe a custom of representing the progress and the status of a proof by what's known as a dependency graph, where every lemma or every statement in the proof is given a node in a graph, and nodes are connected to one another kind of with an edge if one statement is used in the proof of another. And so you kind of get these kind of relationships, these logical dependencies, you can kind of visualize them now at a glance. And the nodes themselves will be colored either green if the proof of that statement has been formalized, or either white if not, and I guess maybe kind of yellow represents some kind of partial progress. And it should also be mentioned that, yeah, so here you see kind of a number of nodes in green, and there's maybe a central node which would correspond to this medium strength prime number theorem, but maybe there are other results towards like the classical prime number theorem that still had yet to be filled in. And
Can you say something about like what they were missing? Like, is it did they just get a different zero free region, or was it?
so they didn't prove a zero free region at all.
Uh-huh.
So they, I mean, so essentially the the weak prime number theorem is also equivalent to saying like there's just strictly for real parts bigger than 1, then you can have no zeros, and that's quite elementary to do actually. But you can translate it in a kind of language about the zeta function without too much effort. And then they found this kind of melon transform. They kind of use some kind of I would say intermediate techniques that could push a little bit to imply some statements about counting primes, but didn't explicitly prove this kind of classical zero free region.
But do you know, I mean, like this must be equivalent to the statement about the existence of some zero free region, right? Do you know, I'm just curious what the shape is.
I actually don't think that's the case. I mean, I think the technical aspect is that if you know if you know a zero free region, it is sufficient to then prove a statement about the distribution of primes. But they found a kind of way where you can actually take some statement about, like, let's say, bounding the logarithmic derivative as some interpolation just based on knowing that, I guess, the kind of classical kind of Dirichlet series for zeta is defined for real part bigger than 1.
Oh, I see.
Something like.
Cool. Thank you.
And so there's like this kind of interpolation. Almost think of like an intermediate value theorem where you kind of integrate from like 1 plus epsilon to like 1 minus epsilon, and you bound the integrand of like the log derivative. But like you don't actually need to prove like a zero free region. That's my rough understanding.
Thank you.
Yeah.
Can I
But
can I ask about this dependency graph?
sure.
So is this something which has been created by Lean, or is it something which the kind of people who are, I think, coordinating the formalization project have put together as saying this is how we're going to do it?
Yeah, so I think it's not part of the language itself, but on GitHub, for example, there have been kind of packages developed by the community to input like a Lean file, and I guess there may be some extra annotations one might need to put in, and a corresponding LaTeX file of like the informal mathematics, kind of guiding the structure of the proof. These are so-called blueprints, and from that data, there is a kind of maybe like a Python script or something that can construct this graph. And then this kind of became like standard practice in the community, in the formalization community, as a kind of easy way to visualize like the progress and the status of a project.
Okay, thanks.
Yeah. So with that kind of as context, the main result I want to talk about today is a new proof of, well, a formal proof of the so-called strong prime number theorem, this full classical result that was able to be accomplished in 3 week of computation and interaction with human oversight, where the agent Gauss was able to work autonomously for hours at a time and kind of liaise with, in this case, me, a human expert. And this was previously quite a laborious process. And along the way, Gauss was able to formalize this key missing result in complex analysis, namely the zero-free region for the zeta function, as well as kind of a number of also very basic kind of complex analysis results you might see in a graduate course. And this also opens up kind of potential kind of future projects that also use complex analysis, which had been kind of bottlenecked. So for example, I had given a talk at this conference in Cambridge at Big Proof in June, in which Marina Wiazowska had kind of talked about wanting to formalize her paper on sphere packing in 8 dimensions. And in that paper, she really needs some results from complex analysis, which kind of was holding up a lot of the project. And maybe hopefully these kinds of tools can be used for other projects like that one. And if you're interested, this proof is available on GitHub on a public repository through mathinc /strong PNT. And I maybe want to say a few words both about the kind of the production or the kind of the workflow of how this artifact was produced, as well as some kind of information about the artifact itself. And so maybe just kind of first at a high level, you should think of there being kind of 2 basic artifacts. One is a document in LaTeX, and other is a document in Lean. And the kind of workflow that I ended up interacting with is that I would produce a LaTeX file. So as a lot of people know, mathematicians really like to use LaTeX. I guess some computer scientists do too. So currently, Gauss takes the kind of agent takes in as input a natural language LaTeX blueprint that's supplied by the human being, and requires kind of, I would say, high-level guidance as this initial document is further developed and refined in the course of formalization. And so maybe as a kind of way to think about this, so you'd start with some human-level LaTeX of a proof, maybe, let's say, from a textbook that you might, or a kind of a paper you might find, or your kind of class notes. And this starting point kind of gets refined informally using kind of human oversight. So in my case, having a sense of how the proof goes, I might want to add some details in certain places. And based on that initial informal mathematics, Gauss would then take this and start formalizing statements. So this actually turns out to be a quite easy process that takes only a few minutes, or sometimes maybe like a half hour. And what this amounts to is taking essentially all the lemmas in the blueprint and converting them into formal Lean statements. So
if I can pause you, I'm
sure.
a bit surprised to hear that this part is easy. Because how do you check the statements are exactly what you want? Like every time I hear anybody else, they're like, this is probably the hardest part, because you have no idea what you have formalized.
Yes. So this is exactly what I was going to say. So it is very easy for Gauss to produce candidates that compile. So producing code that kind of passes the verification check, like syntactically. But I don't know exactly who in the audience asked the question, but precisely as was mentioned, there is a distinct but very important step of validation, which means kind of looking semantically, does the statement that is produced and it compiles, does it correspond to the informal mathematics that we wanted it to? Or does it differ in certain, perhaps subtle ways? And then you would need to make
that? Yeah. So what
and
is
then that would require further revision. So this is where I bring to bear my expertise as a number theorist and look at these statements. And so maybe I should also say that I'm not a programmer myself. I'm not a Lean expert, but I do have a kind of reading knowledge. So I would say like my abilities in Lean are primarily read, not write. So it would be very hard for me to tell between 2 similar looking Lean statements if one's going to compile and another is not. So syntactically, it's maybe hard to say for me, but kind of at the kind of semantic level, at least it's not too difficult to kind of infer the kind of meaning of a
Well,
particular
you have to kind of
mathematics.
trust yourself a little bit to be expert enough to like, I mean, it's kind of, I imagine it's easy to have sentences which are almost correct, or to a human eye, they look correct because the language is kind of not familiar to you. So you're missing the semantic differences.
Yeah, exactly. So this is really where, I mean, as a kind of card-carrying number theorist, I'm really bringing to bear my knowledge of the prime number theorem. So, about taken when I was a first-year grad student, I took analytic number theory, and I've then TA'd and then now taught the course several times. So I'm really, definitely relying on my detailed knowledge of the informal proof when making this evaluation, and making that the semantic meaning is aligned with what we intend. But
So can I ask a couple of more questions? So,
sure.
so you're using some kind of a LLM to do this, or did you just by prompting it correctly, or have you done something else? Like,
Yeah.
what-
So so number one, I'll say yes, there are LLM components, but I'll also get into some of the engineering aspects in a couple of slides.
and then the answer is like most of the time they're correct, or almost 100%.
Yeah, exactly. I'll also mention
You'll
this.
get
So
to
most of the
okay, thank
time when you're running statements, but yeah, let me just say this in a second. I'll return to your question.
Okay.
But once, it kind of just as a kind of high-level overview, it turns out once you have a set of informal lemmas, it's quite easy to produce candidates in formal code that compile, and then requiring human oversight. In this particular project, since I was working very closely with the prime number theorem, it was easy for me to kind of validate the semantic meaning. And usually the semantics would map up quite nicely, and maybe occasionally there would be issues that I would have to resolve. Sometimes there would even be typos that would have come from me that would need to be resolved, and sometimes Gauss would actually make some kind of comment about this, and that I would then go and correct. Other times there are actually quite a bit more subtle and mathematically substantive issues that I'll talk about a few examples in a few slides, but really this also occurred. But once you have these statements that have been verified and validated, then this becomes a goal for which Gauss starts to try to search for kind of produce formal proofs. And for this, once the kind of statements as the goals have been specified, then Gauss would often run for maybe, let's say, half an hour to an hour, and then produce usually, so it might vary depending on the field, but at least for working with me back in July, it was able to get about, I would say, 50% of lemmas within the first half an hour to an hour. And then running over the course of the day, over the next several hours, it would be able to get, I would say, about 90 to 95% of statements. So this means that there would be proofs or missing from the last 5 to 10% of lemmas. And then this would, for these these more difficult technical lemmas, this would be an indication that I should go back to the LaTeX and revise the statements and split them up and decompose the proof into further sublemmas. And then that would become kind of the feedback I would give for me. And after I make that revision, then I would iterate and repeat this process. And I really viewed this as kind of like a dialogue where, so previously I had previous dialogues with human formalizers in which I had a particular paper of mine that I wanted to formalize. And so I would be kind of engaging in a conversation with the human kind of expert coder, and they would be asking me questions at certain points about certain things that didn't make sense. And oftentimes when they'd ask these questions, it actually turned out that what I'd written down is actually literally wrong, and so I'd have to kind of make some revisions along the way to actually correspond to what I had intended as the author. And this kind of mode of interaction, I think, was quite similar to interacting with like a human expert, maybe on a kind of accelerated timescale. But the nature of the interaction where both the informal and the formal artifacts are kind of getting revised along the way. And since then, we're also working with some kind of projects in other areas that will kind of in like beta testing, where Gauss is kind of working more autonomously or more at a kind of closer to human level of abstraction, where less kind of revision and decomposition is necessary, and it's able to kind of work more autonomously. And we anticipate going in the future that there'll be kind of less kind of detailed human oversight required. But for this project, I was back in over the summer, I was quite engaged over a very intense 3-week period, working kind of like 8 to 10 hour days in very close dialogue. So maybe
Jared, before you move on, just so I did look a little bit at the blueprint, and one thing I was kind of impressed by was that a lot of the proofs were like, lemma 17, blah, 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 proof use lemma 16 with not really a lot of details. But so are those examples where Gauss kind of one-shotted the lemma, like where you just like write, basically trivial and it does it?
yeah.
Or
Essentially, what I at least this was back in July, kind of workflow that kind of seemed to be working for me was essentially to make like a LaTeX representation of essentially of a dependency graph with the associated statements. And so the proof would just literally consist of what are the edges connecting. And so that's like a lot of the work I was doing, kind of to kind of put it in this format, and it was working quite well. But I should say that like now, actually, like that level of detail is maybe not even like necessary to do. That you don't need to be working so intensively over weeks. But yeah, really taking in kind of information of the dependencies, and then maybe even like putting some hints in the LaTeX for Gauss to read as it's kind of chugging along and trying to prove these results. This is kind of very much the style that seemed that was working for us. Yeah, so I should also kind of maybe take a moment to talk about the final artifact that was produced. So Gauss generated at the end of the project, after 3 weeks, about a 25,000 line lean code proof of the zero-free region for the zeta function. And then this gets plugged into the previous work of Alex and Terry. I think there's about maybe like another 8,000 lines that relates information about bounds on the logarithmic derivative. So once you have the zero-free region for the zeta function, then you can quickly get bounds on the logarithmic derivative by standard techniques. And using that, this kind of then plugs in modularly to the other work that Alex and Terry had, which can then upgrade. I guess they had a further like 8,000 lines of code. So maybe about in 30,000 lines all combined, this gives a proof of the classical error term of the prime number theorem of Audemars de la Poussin. And here we can maybe see a bit of a more detailed kind of dependency graph of all, I think about maybe on the order of 70 statements of lemmas and definitions. And this, yeah, about 1,000 of them. And you can see that in particular, all the nodes are green. And if you kind of squint there, you can see maybe some lighter green square boxes, which correspond to definitions. So they don't themselves have proofs, but their statements of the definitions have been formalized and also validated. And really, one of the kind of maybe almost complexity theory viewpoints maybe you might take is that really, if you just look at the end statement and you validate it, as long as you have some compiling proof, then you're kind of assured that the statement itself has been proven. I should also mention that maybe looking forward, there's a distinction between having a compiling proof versus having maybe an understandable or a more kind of compressed, compact proof. And this is also an important objective to be kind of interested in. And so the kind of library in Lean makes use of very compact proofs, which so even before us, Alex had been talking about since the medium prime number theorem, wanting to then take a pause in the project before going to the strong prime number theorem and trying to kind of refactor and compress the code that they produced to make it more modular and amenable to being used repeatedly in the library. So yeah, I should say that this is by no means the most compact proof, and maybe the proof done by a human might be shorted by a factor of like 3 or 4. But in any event, this is a compiling proof. And I should also mention that proofs at this scale had historically, of thousands of lines of code, have historically been kind of notable milestones in the history of formalization, which are often the culmination of multi-year efforts by groups, not just individuals, but groups of human formalizers. And perhaps for some context, so Gauss was an agent developed over the summer, a prototype of which we announced back in June at this big proof conference in Cambridge, for which Gauss, a prototype of Gauss, an earlier version, was able to produce a 3,500 line proof of a result of actually relating to the ABC conjecture on average. And that result itself was about an order of magnitude larger, as at least counted by the number of lines of code, any prior automated effort. So if you think about, at least from the beginning of the summer, a lot of people had focused attention on competition math and maybe problems like from the IMO or something. And so for these competition math problems, you could get solutions that might be like 100 or a few hundred lines of code. And so 3,500 lines represented maybe about an order of magnitude larger than previous efforts. And then so the more recent results with the prime number theorem represents maybe 2 orders of magnitude larger. And for context, at least counted by lines of code, the largest formalization projects that have ever been done, these essentially are these career-defining efforts spanning, in many cases, over a decade. So think about examples like the Kepler conjecture, or maybe like the odd order theorem, like the Phi-Thompson theorem, that these were about maybe 300,000 to 500,000 lines of code. And in the case of the Kepler conjecture, it took Tom Hales and his group over a decade to formalize. So this is really, a really serious effort. And further for context, so mathlib is the kind of standard mathematical library for Lean, is only just essentially 1 order of magnitude larger, is about 2 million lines of code, which comprises about 350,000 theorems and definitions, which has been developed by hundreds of human contributors over 8 years since it was formed. So really, that's maybe 2 orders of magnitude larger than this particular effort. And
Sure.
so,
So with the ABC almost always result, like the 3,500 lines of code, can you spitball like how many lines of code it would be if a human like made enough?
yeah, so I talked to
make it
my
compact?
maybe as some backstory already, like this particular result, I'd previously been talking, before getting interested in auto formalization about using AI, I'd been just interested in formalization in general, and I'd been in contact with my friend Bhavik Mehta, who's one of the kind of world experts in formalization, and he looked at the code at least back in June and said, oh, he could probably do this in 1,000 lines. This, this is about 3 to 4 times more verbose than maybe what an expert might do.
Thank you. That's
Yeah. So maybe this gives a sense of scale of this project in context. But I also maybe now want to turn to the mathematics itself, and also regarding one of the questions that was mentioned about this question of like validation of kind of semantic meaning. And I also want to kind of stress at this point that this is also one of the benefits of formalization, where really one's feet are held to the fire, and one is really kind of forced to actually learn the mathematics and a lot of the details that go into a particular proof. So as I mentioned, I'm a number theorist, and so the prime number theorem is something I've both learned and then taught multiple times. But I might feel a little bit embarrassed, but I should mention that for each time, both in the notes and in textbooks, you kind of have some kind of exciting number theory about counting primes, for example. but then there would be like this kind of short appendix at the end where you'd like state a bunch of results from like complex analysis, which you kind of brush under the rug and say, oh, you know, this is like a standard reference, so we won't get too much into it, and your kind of eyes would glaze over, and I didn't actually know too much about the details about these results, and I would just kind of like cite them as a black box. But really, in the course of this proof, I was forced to really learn the details. And so in this way, this act of formalization was also a very kind of pedagogically interesting activity. So in particular, I want to stress that one of these kind of core results that were kind of needed in the proof, the zero-free region for zeta, is the so-called Borel-Carath&eacute theorem. So this is a technical statement that you might see in a graduate textbook in complex analysis. So it's stated as follows. So you have two radii, little r and big R, less than 1, and a function f, which is analytic on a disk of radius big R. So you have this nice function f on a disk, and you assume that all values of the function, or all values of the function have real part bounded by some constant m. So essentially on a smaller disk of radius little r, you have the function being bounded, and it's defined on the kind of on the larger disk and where it's analytic. So if you're in this setup of a nice function with bounded real parts, then the Borel-Carath&eacute theorem says that the modulus of the function should also be bounded in terms of m and the two radii. And maybe a way to interpret this statement, so it's a technical statement, but a way to interpret it is that if you think about the modulus, or the modulus squared, as being like the real part squared plus the imaginary part squared, and then just up to constants, this is essentially telling you that, so this is essentially relating the real part and the imaginary part. So if the real part is bounded, then the imaginary part is also bounded up to constants. And so maybe kind of conceptually what you might think is that for an arbitrary complex number, you have a real part and an imaginary part, which could be thought of as like two independent variables that have nothing to do with each other. But if that complex number is actually the output, the value of some nice function, nice analytic function f, then there needs to be some kind of constraints and relationship between the real parts and the imaginary parts of the values of our function.
So just to myself, is this like, it's like the Schwartz lemma, except the target is a vertical strip instead of a disk? Is that...
So I mean, this particular result uses like the maximum modulus principle. Maybe I don't. Maybe that itself.
Anyway, that's all right.
But I mean, yeah, these are kind of these classical results in complex analysis that you can consult like a reference text for this. Yeah, so in this case we use like the maximum modulus principle to prove Borel-Carath&eacute, and a lot of this was not in the in the Lean library. That needed to be kind of built up from the ground up. And also once, in particular, so once you prove a bound like this for f, it turns out you can use like the Cauchy integral formula to actually bootstrap this to get a bound for f prime. And so this was also another, like the Cauchy integral formula is something that you also need in Lean. And so in particular, so as Daniel mentioned with this logarithmic derivative, the application we really have in mind for using Borel-Carath&eacute is when our function is the logarithm of zeta. And if you then take the...
Can I ask a question?
Yeah,
the
sure.
statement looks weird to me. I'm missing something, I think. Like, what if I pick the f to be the identity map and then let the capital R go to infinity? Looks like the f becomes, yeah.
So R has to be less than 1.
R is not 1. I see. That's what it is.
Yeah, that's very important.
So R is not going to go to infinity. Okay, thank you.
Yeah, okay. And so in our application to the prime number theorem, I mean, so the Borel-Carath&eacute theorem is just a general result in complex analysis. For our particular application to number theory, we are going to make the choice of our function being equal to the logarithm of zeta. That's what we want. And then, as Daniel kind of alluded to, we're off to the races. If we take the derivative, we get the logarithmic derivative. So this becomes f prime over f, or in this case, sorry, zeta prime over zeta. And then you can start doing things and relating it to prime numbers and such. This is like the high-level idea and of what gets the proof really going and what Riemann really had a vision about. But really, in practice, there was a lot missing from MathLib, a lot of even very basic theorems that I didn't even know to kind of even have to kind of cite, that these are almost like the water that you drink, that is just so kind of embedded in the way people think about these kinds of proofs, that they were nowhere mentioned in the kind of mathematical notes that you'd get in the proof of the prime number theorem. So for example, something like this is that a function, this analytic function, admits a complex logarithm. So this is a very basic statement, that you want to be able to take the logarithm of zeta and have this be itself as a complex function, a nice kind of function with nice properties. But this wasn't kind of, number one, it's not going to be mentioned in a human informal proof. And the statement of this is like something technical relegated to like a graduate text in analysis. But even to do that, so this was also missing from the library. But even to do that proof, one also needed to prove that analytic function admits a primitive, admits an antiderivative. And so this is essentially like the fundamental theorem of calculus for complex analysis, which was also missing, to my surprise, from MathLib. And so we had to essentially devote the last week of our project to proving these very kind of fundamental results, these very basic results that you'd find like in the first couple of weeks in a graduate course. And so this maybe gets to a sense of the question. And a colleague, Emily Riel, has a very nice phrase for these kinds of settings, which she calls invisible mathematics. This is kind of the implicit assumptions that all the kind of human experts kind of carry around as being very obvious, but in the course of formalization, one really needs to make these kind of subhuman, kind of invisible mathematics and bring it and make it explicit so that it can be brought to bear. And this was definitely a case of this invisible mathematics, which I didn't even think as an assumption that this was something that needed to be proven. It was just kind of like the water that you drink. In this particular case, there are actually several like subtle aspects that also I kind of needed to infer based on my interactions with Gauss and kind of using my domain expertise. So in particular, there are various setups using these radii. And actually, in the course of proving results using these various complex analytic constructions, you actually need not just two, you apply this result and similar kinds of results in multiple places. And each of these statements have like two radii, a little r and a big R. But it turned out that with a bunch of these statements, you actually needed many more radii and apply them for different instances. And so actually in the specific proof, we actually needed an R1, an R2, R3, and R4. So we needed 4 different radii running around. And you'd specialize them depending on which technical result you needed. And so this was never mentioned in any kind of human-style proof. Is that it's always assumed that you know what particular pair of radii you're looking at. So that's maybe a low-level kind of comment that was really needed to understand semantically, as maybe a subtle point. But the really kind of even more fundamental point, mathematically, conceptually, is that in the proof of that a function admits a complex logarithm, you need to kind of essentially take a branch cut. So essentially, one of the whole motivations for the field of complex analysis is to really understand like the logarithm, the complex logarithm, and really what you do is that you say, this function is not defined on negative real numbers, and you kind of cut away this line segment from the complex plane, and after that you can define the complex logarithm. But really, when you actually are applying this in the case of the zeta function, and you cut away this line to make sure that your function is never 0 on that kind of negative real axis. But when we're actually applying this to the case of the zeta function actually has trivial zeros that are located along this negative real axis. So really, the standard kind of proof of taking of how one constructs a complex logarithm actually fails in this case. And so this actually required in the last week of our project to really go in and actually have a different construction of the complex logarithm. Actually, there's a more general construction that one needs that uses not just kind of using the negative real axis, but takes an arbitrary kind of like branch cut that as long as you have some curve, which maybe starts at the origin and goes off to infinity, maybe at a different angle, and maybe it kind of wiggles, but you need to take some other branch cut, and then using that given curve, you can define the complex logarithm. And that's really what we needed. We needed this more general version of not only getting an antiderivative, but also then defining a complex logarithm with a different kind of branch cut. And this was precisely the kind of result that was not in the kind of standard textbook, not in the kind of refined proof that I originally developed. This was born out from kind of my domain context with Gauss's interaction informing me that, this is failing for this particular reason. And in fact, the original kind of lemmas that I were trying to prove were in fact false because they're not defined for zeta. So this is the kind of style of maybe really having my feet brought to the fire, of really having to understand all the details of the intermediate steps in the prime number theorem. And so for that, I would also say this was a very kind of educational process for me.
So Jared, for something like that where you have to have some lemma with 4 different radii or whatever, is that something that Gauss is helping you with, or do you kind of still have to formulate this sort of more complicated statement yourself?
Yes, so this would be using my kind of domain expertise to formulate the revised statements.
So having discovered that you had to have, discovering what the invisible mathematics was that you needed to make visible, is all of that now available in MathLib so that the next person who comes along trying to prove an adjacent result doesn't have to go back and prove all those things again?
Yeah, precisely. And this is one of the main purposes of formalization is that or like in math, in principle, you want to prove something, you prove the Pythagorean theorem, then it's true forever, and then anyone else can use it. And so that's like what's, maybe philosophically, in principle, what mathematicians are doing. But actually now, with having compiling code, you literally can modularly take results from previous projects and then as needed take it to your next project in the future. And so that's literally one of the kind of central motivations for a project like this, is to use some results in complex analysis for other projects.
So what we see happening is that people are kind of coming in with a big project like formalize the proof of the prime number theorem, and in the process they have to develop all of these preliminary results. It's kind of like backwards to the way that mathematics is developed organically, except that at some point so just even getting the basics down, somebody had to do it. There's just defining what is a complex number.
Yeah. So some of those things were already done in MathLib, and we rely on, like, the proof relies on a ton of the previous results in MathLib. So you can say like this whole project has dependency on MathLib. But there are some basic, sometimes very basic theorems, like that there's an antiderivative, which I had to kind of put in the course of my proof. So I had to kind of back solve for some things. I might also push back on the point you made about how mathematics is kind of naturally, organically growing. So sometimes, like, you have some result that you want, and then maybe you have to fill in some background and material. So I'm thinking of an example like the Weil conjectures, where there was geometry in like a classical complex setting where people had done a lot of work, but then people would want to prove like analogous statements like for a different ring, and then you would need to actually develop an entire field, an entire theory that corresponds to the analogous kind of basic results, and no one had done that before. And sometimes like the analogy of the existence of previous kind of results in a different setting would motivate actually filling in the basic results kind of after the fact. Maybe Daniel knows a lot more than I do, but I think there's also like a kind of symbiotic relationship between various levels of abstraction.
I fully endorse your pushback there, Jared.
Yeah. But yeah, it's definitely true that like
caveat, yes.
yeah, that you're very correct that we needed to prove statements that are more primitive and more logically dependent on subsequent things, but the order in which these this code is instantiated may vary. Your mileage may vary. So I also maybe want to say some words about kind of maybe the infrastructure and the engineering, which is maybe the unsung hero in this whole effort. So key infrastructure for this effort was provided by with Morph Labs previously in the summer of using kind of so-called Trinity environments, which are these kind of lean environments. So a human working in lean, maybe put in VS Code or something, but you can kind of see the status of maybe a proof in lean or a partial proof in lean, where you have like some goal and you have some tactics that you could do at any given time to achieve that goal. And what you should think about is Gauss had access to this kind of environment that a human would have and be able to kind of see the state of a partial proof and then be able to try various options in the course of the proof. And in fact, not just trying one option, but kind of splitting off in parallel and having many instances of Gauss trying to prove various of these options. And really the unsung hero of this is these kind of infrastructure for having the so-called scalable lean verification environments where yeah, so this is a very outside of my expertise, but this is kind of a complex systems engineering challenge, which really can only be accomplished, I think, using kind of industrial scale computation, which definitely previous to being in academia, this is not something that we necessarily work about, but the kind of mental model that you might want to have is think about having thousands of instances of Gauss spawning to try to prove a particular result, and each having its own kind of environment and lean runtime, and using terabytes of a cluster of RAM, and this so-called like InfiniBranch technology developed on the Morph Cloud was critical to the success of this project. And as the goal, we're MathInc is now trying to make these results useful, this kind of technology useful to mathematicians and proof engineers. And presently, we're kind of in contact with an initial group of mathematicians for beta testing. So, for example, we have a project with Terry Tao doing explicit results in number theory. There's also a result with Professor Melanie Wood working to do class field theory. And we're also very much open to other suggestions about working on projects. And yeah, just feel free to send a message either about getting early access and hopefully in the next coming months, we'll be able to open up further and maybe have an API or something like some kind of usable tool, which just people, kind of working mathematicians in the community can actually make use of. And so maybe the phrase working mathematician is kind of an ode to a previous textbook called Category Theory for the Working Mathematician, where category theory is this field where people have make use of a lot of results, and it's useful in many applications, but maybe only a subset of people actually know the internals of the field of how it works. And so there's like a modular component where one wants to have some sort of familiarity, but not necessarily domain expertise. And we view this as a very similar kind of motivation to have future efforts make use of kind of formalization technology without necessarily needing to know how to formalize. And yeah, so we really view this result with the prime number theorem as like the first step towards kind of formalization at an industrial scale that people in the community can make use of, like with tools. Yeah, similar in the kind of way that now, like if you pay $20, you can get like GPT-5 or Claude or Gemini, something like this. And so with additional kind of computation and algorithmic improvements to Gauss, we anticipate to actually increase the sum total of all compiling code in the library by orders of magnitude in a very short time frame. And maybe in the interest of time, I'll close there. But if you have questions, I also have some thoughts. Slides I could have gotten to on mathematics in the future. So with that, I thank you for the time.
All right, let's thank Jared for that great talk. So we are a bit over, but I think, Jared, if you have time, maybe people who are able, we can give people who need to go a chance to go, and people who
Sure.
stick around can ask some questions. Yeah, so does anyone have any questions for Jared? So I have a question, which is, can you tell us about mathematics in the future?
Yeah, all right, thank you so much for the additional time on the floor. Really, I think maybe the part of the motivation for a seminar like this is to try to think about or try to kind of envision positive futures for what this kind of new technology might start to look like in the future. And maybe to ground ourselves in this discussion, I'd like to think about kind of maybe the activity of mathematics historically and try to connect it with potential modes of interaction in the future. So this kind of project and this kind of perspective really kind of has reinforced to me the idea that mathematics is really at its core a knowledge base. So this knowledge has been accumulated for hundreds, sometimes thousands of years, and each new result kind of gets incorporated into the kind of knowledge base. And for example, the Pythagorean theorem, right? It was proven thousands of years ago, but it's still used today in many results. And so once a new result is proved, it's true forever, and then can be built upon by later contributors. And the recent development, the recent movement of formalizing results in Lean and other languages in compiling code is really a kind of computational equivalent of digitizing this knowledge base into a kind of compiling code of a formal database. And the artifacts in which, as we've kind of seen with the dependency graphs, really are a kind of a graphical structure that we're encoding using the theorems and definitions, also conjectures of these nodes that have yet to have a proof in them, where the edges between these nodes encode the kind of dependencies and the logical implications between these things. And I would argue that given such a knowledge base, given such a kind of graph or hypergraph, the kind of central objectives of this graph are of expansion and of compression. So these two objectives are distinct, so they're also kind of in tension, but they're also reinforcing each other in feedback loops in important ways. So by expansion, I really mean thinking of adding new theorems and kind of adding new theorems and lemmas to the database to expand the graph. And in particular, we're not just interested in one could be interested in arbitrary statements, but oftentimes one is motivated by influential or important statements. And that importance or influence is actually kind of maybe thought of as actually a graph property. Kind of those that have edges connecting to other results in the database. So in particular, like the case of the Riemann hypothesis, there are many textbooks that are written, maybe thousands of pages of ink spilled on assume the Riemann hypothesis, then you write this entire thousand pages of mathematics. And so really the kind of importance or the kind of value of the particular statement can be encoded in the kind of graphical relationship that the Riemann hypothesis has all these downstream kind of logical implications. And so like a lot of the activity of mathematics is incorporating these new statements which have kind of relations and kind of dependencies to other existing kind of historical pieces of mathematics. So on the other hand, besides adding new results, another central objective of the practice of mathematics is that of compression with a database, and that of you can think about like a code base where you synthesize and refactor this code base. And so this could consist of maybe at the most simple level of just coming up with maybe tactics or even just defining variables to improve efficiency. So if you're repeating the same string over and over again, maybe you have a variable. If you're repeating the same kind of few chains of logic over and over again, maybe you encode it that kind of as a tactic. And so that's just a way of simple kind of like abbreviating and compressing these repetitive things. But maybe since Daniel is in the audience, maybe a deeper interpretation of compression is really coming up with the right abstractions, coming up with the right definitions that really kind of can encode even entire swaths of patterns across different disciplines. And then if that is codified in an explicit definition, then this can give an explicit kind of dictionary between various fields, as in the case of the Weil conjectures and with Grothendieck, he was really kind of revolutionizing geometry back in the 1960s and relating it to algebra and topology. And really the way I'd like to think about, or way I've come to think about this kind of revolution of Grothendieck is really he essentially refactored the code base of geometry and algebra and topology, and coming up with the right kind of code and the right abstractions that really kind of synthesize these formally disparate domains. And so I really view that kind of achievement as one of compression. So I would say a lot of the kind of activities that are valued in the mathematical community are obviously like proving new theorems, proving exciting theorems, kind of expanding this knowledge base, but also taking the existing knowledge base that we humans have constructed and actually refactoring it and which will give us new insights. And like Grothendieck is one of these kinds of examples that I really kind of have in mind with this idea. And so just maybe in my last slide, I want to kind of emphasize that, or maybe my point of view has come to be that these two activities of expansion and compression are really kind of, I would say, are going to remain invariant with us, because these are kind of graphical, these can be kind of represented kind of intrinsically to the structure of the knowledge base itself, and will remain going forward. And whether our human beings are expanding or compressing, or whether machines will be aiding or working autonomously, these will remain the kind of two core objectives. I've gotten some maybe pushback in the past about maybe this kind of perspective, but I also maybe want to kind of engage in this this kind of critique that people often talk about, especially in the practice of mathematics, is one's kind of individual perception of kind of subjectivity of the kind of beauty of the results they're proving, or the importance that different people have different opinions of what is beautiful or what is important. And my kind of emerging viewpoint on this is maybe to say that no one knows all of mathematics, and you know, it's not since maybe 100 years ago, since the times of like Hilbert or Poincaré, where like an expert has been said to kind of understand all the fields, at least at a certain level of abstraction. And maybe, you know, someone like Terry is approaching this by knowing like maybe almost half of all of mathematics or something like this. But each of us only know a small corner of mathematics, and one can view as so one has the kind of explicit knowledge base of kind of what's represented in the literature and in textbooks, and this is kind of this common knowledge base. But each of us individually in our heads has only a kind of very small subgraph of that knowledge base, and maybe it's also maybe corrupted in some ways in our misunderstandings. But it is specifically the different subgraphs that we each have in our heads, which is informing our evaluation of what is beautiful and what is important. So how it relates to this marginal new theorem, how it relates to our particular subgraph, and maybe understanding new definitions and concepts, really the extent to which they compress and refactor our particular subgraph is maybe pointing to our subjective experience of what is beautiful and what is important. So this is maybe you can think of it as being like a relative property. So specifying a given subgraph of the entire knowledge graph, what is this kind of graphical kind of statistics of the marginal expansion and compression is maybe what I'd kind of point to in this direction. And I should also mention that, you know, mathematics is still developing. It's an infinite subject. And so at any given moment, any of us, or even the kind of collective of humanity, only has access to maybe a large subset, but within the large infinite subset. So this also can be changing over time. And, you know, people talk about different trends in mathematics. This is when the entire community has like a certain aspect of what is valued as a subgraph, and then if some new marginal piece of information comes in and that changes maybe an entire field's perspective on what is important, this can be also viewed in the same kind of relative sense. And I want to I really feel that these kind of properties are really intrinsic to the activity and the kind of structure that one is building, and that this will remain whether the practitioners are humans or machines. And I think the hope is that we can maintain like a dialogue, and having some maybe continuous or relatively comprehensible iteration of one subgraph to the next, that we can kind of maintain with this as capabilities advance with models, that we can still kind of share insights, and as you know, advances progress, we're still gaining value from this activity. And so that's the kind of closing remark I might make at this point.
Thanks so much. Other questions for Jared? Looks like.
Hello? Can you hear me?
Mm-hmm.
Yeah, I got a question. Thank you very much for your very interesting and inspirational talk. Maybe you can give an insight based on your experience working with Gauss, if it had like a preferred subject, in the sense that it was easier for him maybe to formulate statements in combinatorics or in number theory, or more
Yes.
arithmetic statements compared to geometric ones or something along these lines?
Yeah, so I should first mention that it's an evolving subject, and I only have a experience with a small subset of subjects. But I should say that the way I maybe like to think about this is thinking about maybe Gauss as being some sort of kind of translator. But depending on what side you're on, like if the kind of expert knows very well and has very kind of strong attunement to a particular field, and then can bring to bear their own human insights and their own kind of human understanding of the content, then the active translation will run more smoothly. And so I should say that prior to this project, complex analysis, or still kind of is viewed in the community as a very kind of technical subject that was very difficult in Lean. And Terry and Alex spent a year and a half trying to do this. So it's by no means an easy subject, but at least in my experience, and now working with some beta testers across various subjects, I'm coming to maybe the view that the success of an effort like this would be a kind of a function of the kind of human's level of knowledge and the particular result, and maybe also their willingness to work for extended periods of time in a dialogue. But so far, there hasn't been necessarily any kind of inclination to one particular subject or another.
Okay, thank you.
Daniel, you're muted.
It looks like Shuji has a question.
Okay.
I think people should just unmute themselves and ask.
Okay, yeah. Yeah, thank you for the wonderful talk. There's one question regarding the basically it's quite surprising. On one hand, it's very surprising to see that the 25,000 proofs can be roughly automated generated by these foundation models. But also another part also surprising me that you mentioned you have to spend 1 week to figure out some seemingly trivial properties proofs. And then the question is why that last week of effort cannot be automated and wouldn't make it particularly challenging for the foundation models to achieve that?
Well, I mean, so when I mentioned the last week, it spent a substantial part of time trying to prove actually like things that were wrong, and they were wrong because of my incorrect understanding of the proof. And in the course of this interaction, I realized my kind of errors. So if put garbage in, you're going to get garbage out. Really, the kind of limiting factor in this activity at that point was my incorrect understanding of what aspect of the complex analysis that needed to be formalized, and we were actually doing something with the wrong branch cut. So identifying, that you're often that the proof strategy itself is off in a wrong direction is something that if Gauss could have automatically discovered that, that'd be great. But certainly, I would say the better that, or the more kind of comprehensive kind of the mathematical content is understood, then the active translation will go more smoothly.
I see. So basically, when I have my background is more in CS, not in math. It to me sounds like if you have a wrong specification, there's no way for you to give a correct implementation because the specification itself is got a flaw.
Yeah.
Okay, I see. Yeah, so it really take a while. Okay, I see. So when I feel that it's tricky that maybe the theorem itself not formalized correctly, or maybe there's some missing assumptions, then you have to manually identify those parts.
Yeah, exactly. Yeah.
Okay, awesome.
But some of them also, as I mentioned with this invisible mathematics, some of them are never stated as assumptions. One has to kind of discover that they're actually like these implicit assumptions that one needs to add that are kind of maybe quote unquote obvious to experts in context. But to actually bring them out to the fore is also part of this activity.
Another thing I'm curious is so I quickly go over the general proof. It's quite impressive. I found some are super long, some have really 100 lines proof for just one single theorem. I'm curious what kind of natural language guidance are provided, or is just purely just automated generate hundreds of. I mean, in this case, 100 lines proof. That seems quite impressive. I'm curious.
So some like the kind of LaTeX, you might think of like a proof from a textbook, and then converting that into like a LaTeX file and kind of decomposing it into several steps. And you can view those as like hints or something, and then you can actually identify what previous lemmas are used like in the dependency graph. And that's kind of used as like, hints for Gauss to be starting to formalize. But yeah, as you mentioned, sometimes the proofs will be hundreds of, for a specific lemma, might be hundreds of lines, maybe in a few instances, or maybe 1,000 lines or something like this. But yeah, so in addition to me, maybe a way I like to think about it is that, starting from the human level, I do some work to get down to maybe a lower level of abstraction. Maybe I talk to like a beginning student, or kind of lower to kind of explain things in more detail. But then Gauss is also doing work to like decompose it further in its efforts with, or not one Gauss, but maybe like hundreds of copies of Gauss are separately decomposing and trying various proof paths in the course. So, maybe you can think of like some intermediate level where the human being is doing some work to bring it down to a certain level of detail. And then depending on the area, it'll vary where that detail threshold is. And then the rest of the way, Gauss is like doing further decompositions and attempting to do proofs.
Okay, yeah, that's quite impressive. Yeah, thank you.
Thank you.
So I don't know so much about like Isabelle and Lean and how they compare, but so I know there's another formalization of PNT and Isabelle, and I was wondering if you could kind of compare.
Yeah, so I think it was mentioned that maybe earlier this year there was also like a proof in Isabelle. But yeah, so I don't know much about Isabelle, but I think it was told to me that previous to this there had been a lot of complex analysis previously developed in Isabelle. So I think the proof of that is like actually quite short. I mean, the proof,
like 6,000 lines.
Yeah, so the proof of the whole number theory result is actually not too long, and a lot of the bulk of this 25,000 lines is devoted to proving these core results in complex analysis. So I think maybe there's like some parity there, but actually like to prove those results in complex analysis was something that the lean community had been wanting to do for a long time. So I really regard this prime number theorem as an excuse to have gone in and done like the zero region for the zeta function and doing these core results in complex analysis almost as like the more important objective. And I think those things had already been, maybe like these core things in complex analysis had already been done in Isabelle.
I see. Cool. Yeah. So I also so when am I going to be able to like take the Stacks project or EGA and just feed it into Gauss and get a do you have a sense of where things are going? Like,
yeah, I mean,
if you don't want to make a projection, that's fine.
I mean, I certainly think within like 12 months, something like this is definitely possible.
Okay. So is that a prediction? Like in 12 months, we'll have a formalization of EGA? That would be amazing.
We'll have an ongoing project,
Oh, okay.
which will
I
be
see.
making progress.
But you're still imagining some amount of human involvement, like it's.
I have very wide uncertainty either way. I could see it easily being, either requiring human oversight, or I could also easily see it being just quite automatic. I have a very wide variance. But also, people reach out, Daniel, if you have, want to do like this Stacks project, like definitely this could be a very interesting thing. Like pick like certain specific results that are close to what our prerequisites are, and like try to identify how to, fit this jagged level prerequisites that are in MathLib and try to like fit it into this. Like, I think that could be very exciting as well.
Yeah, I mean, I actually have on my computer, I started writing like a LaTeX document aimed at doing Riemann Rock, but I already felt a little scary to me. So, but yeah, I'm happy to talk more.
So I guess we can talk later, but do you just know off the top of your head like what prerequisites are there and what are missing for Riemann Rock?
I'm starting to figure that out. Yeah, that's a big part of it, is just me familiarizing myself. But yeah, anyway, I don't want to. If there are other people with questions, I don't want to dominate the conversations. Maybe we should say. Are there any other questions for Jared?
Are there any like particular issues like Gauss could run into with, say, the dependent type theory in Lean, or like the very specific Lean specific errors which are maybe not so much related to mathematics?
Yeah, I mean, there are a lot of these. Yeah, there are a lot of these kind of subhuman things. For example, like casting issues come up a ton. So like, whether this number is an integer or a natural number or like a positive net or something like that. This was like consisting a lot of the issues, and like making sure that, any particular statement would be fine, but the compatibility across statements of being the same casting, this was like a recurring issue that we need to kind of deal with and kind of coach Gauss.
Yeah, but in the end, Gauss managed to find its way.
Yeah, I mean, with enough
Okay.
coaxing. Yeah.
Thanks.
Cool. All right, maybe let's thank Jared one more time then.
All right.
Yeah,